Hello everyone, my name is Felix Zahn and I'm a PhD student at Heidelberg University. Today I'm going to talk about network locality in MPI-based HPC applications. Why are we looking at locality? To motivate this a little bit, I found this nice quote of Bill Dully on Wikipedia. It goes, "Locality is efficiency, efficiency is power, power is performance, performance is king." But what does locality has to do with performance? Well, data accesses over the network are usually several orders of magnitude slower than local memory accesses. So if we can understand and exploit network locality of a given application, we can also improve its performance. And in addition, if this results in a reduced network traffic, this could also be beneficial for energy efficient networks. So what is the state of the art? If we currently speak about an application's communication pattern, we usually use metrics such as message or injection rate, message size distribution, maybe also MPI idle times, and of course traffic heat maps, as they are depicted on the right side. This visualization is easy to understand, but how can we objectively compare different patterns? If we are looking at the two examples on the right side, we can guess that both rely on some sort of nearest neighbor communication. But how do they actually differ? Well, the top one shows a two-dimensional nearest neighbor and the bottom one a three-dimensional nearest neighbor communication pattern. But such conclusions are hard to draw, especially if the communication patterns get a little bit more messy. Therefore, it would be useful to have some objective description of these patterns to better evaluate them. So what we did in this work was looking at MPI application traces from different point of views. First, we are looking at the application level. This means we are only considering information provided by the MPI application traces without any additional network data. In order to evaluate different applications here, we introduced two new metrics. The first one is rank locality, which is a measure for the distance. And the second one is selectivity, which is a measure for traffic volume in the network. In the second part of this work, we are looking at the network level, which requires some kind of model in order to derive network-specific features. Based on a simple non-temporal network model, we are evaluating different network-level topics, such as multicore effects, network locality, and network utilization. Here's a short summary about the applications that are evaluated in the context of this work. These exascale proxy mini applications are provided by the DOE to project different kind of communicational behavior used by potential exascale workloads. On the right side, you can see a short introduction of all used applications, which are available at different scales. The traces are provided by the Sandia National Lab, and they are publicly available at the link below this table. However, there are some limitations in these traces. The first one is the usage of user-defined data types. Usually in the here used stampy trace format, information about the size of these data types are stored in header files, which are missing in this repository. Another major problem is the usage of custom communicators that change existing communicators during execution. The problem with these communicator changes is to ensure that linking particular ranks to the identifier remains valid after these changes. Since consistency cannot be assured for these kind of communication, applications that are using these kind of communicators are not considered in the following. Overall, 25% of these configurations rely on collective communication, and the rest mainly relies on point-to-point communication. Let's have a look at the first new metric, rank locality, which is a measure for the distance in MPI traces. First, we define the rank distance as the numerical distance between two ranks, and the locality as its reciprocal. So, longer distances result in lower locality and vice versa. For example, if you're looking at direct neighbors, we have a distance of 1, which results in a locality of 100%. Furthermore, we are only looking at point-to-point communication, since in all used applications there's only global collectives, and they are assumed as an even overhead distributed over the entire network. And in order to reduce network traffic noise, we are only looking at the nearest 90% of the traffic. Let's have a short example to make this a little bit more clear. On the right side, you can see 5 different ranks. If we now send a message from rank 0 to rank 2, that results in a distance of 2 or a locality of 50%. Or if we want to send from rank 4 to rank 1, we have a distance of 3, which results in a locality of 33%. And why is this metric useful? For example, it can help to predict communication patterns. So let's look at the nearest neighbor communication pattern, for example. The majority of the communication in this pattern should happen within a distance of 2, which results in a locality of greater than 50%. If we're looking at the plane rank distance, which is depicted by the 1D column in the table, we can see that there's no application that has a nearest communication pattern. But this doesn't match the assumptions we made in the beginning about these applications. Why is that? Because these applications can have multiple dimensionalities. So let's have a short look at this example. At one dimension, we have rank 2, which has its direct neighbors 1 and 3. This results in a rank distance of 1 and a locality of 100%. If we are now looking at 2 dimensions and rank 7, it has also direct neighbors in 6 and 8, which results in a distance of 1 and a locality of 100%, but it also has direct neighbors in 2 and 12, which results in much larger distances and less locality. However, luckily, these distances can be determined by a constant offset per dimension. For example, in the x dimension, we have 5 ranks, so this is just an offset of 5 to the usual locality. And it works the same way for 3 dimensions. If we are now looking at some example applications on the table on the right side, we can see that there's no application with a one-dimensional nearest neighbor communication pattern. For 2 dimensions, we have in partition one application that follows a 2-dimensional nearest neighbor communication pattern, which is also the example workload from the beginning at the heat map example. And we have in AMG and Lulash 2 workloads with a nearly perfect 3-dimensional communication pattern. And we have in Boxlib and Multigrid C 2 applications that doesn't show any nearest neighbor communication behavior. So in summary, this metric can help to easily identify communication pattern in a formal way. The second metric we are looking at is selectivity. Contrary to locality, this metric focuses rather on the traffic volume than on the distance. In order to determine it, first the communication partners of one rank are sorted by the exchange traffic volume, as depicted on the right side. The number of communication partners that represent 90% of this traffic volumes then equals the selectivity parameter. So in the example on the right side, we have 3 ranks that are heavily communicating with this example rank, and 3 more ranks that only contribute a little to this communication. So this would result in a selectivity of 2.9, for example. We further use the Pierce matrix, which was introduced in another work for comparison reasons, and the number of peers equals the total number of communication partners. So in this example, we would have a number of peers of 6. And keep in mind that the difference between these numbers equals just 10% of the traffic volume. For a better illustration of this metric, this plot shows the trend for multiple applications. The x-axis depicts the number of communication partners, and the y-axis the relative share of the total communication volume for one particular rank. The red line in the top of the plot marks the traffic volume of 90%, and the intersection of each curve with the red line depicts the selectivity of each application. So if we're looking at the partisan workload, for example, it has a selectivity of slightly higher than 3 on the left side, and on the right side the largest selectivity is provided by the snap workload with a slightly higher than 10. So overall we have a very low selectivity, especially compared to the number of ranks that are represented here. Here in this plot you can see the selectivity and the number of peers for all studied applications that rely on point-to-point communication. On the x-axis, the applications are sorted by the number of ranks, so most applications appear multiple times at different scales. The colors in these bars indicates the share of selectivity in light gray, the number of peers in dark gray, and the number of ranks that do not participate in the ranks communication in black. Every metric is normalized to the number of total ranks. On the left side you can see that the relative share of selectivity is slightly higher, which is caused by the overall small number of ranks. However, it remains constantly low when scaling the number of ranks. In total measures, there are only 5 configurations that have a selectivity of more than 10, where 20 is the largest selectivity among all applications. It's also interesting to see that some applications have significantly more peers than their selectivity. However, these ranks contribute only to 10% of the total traffic. To sum this up, the majority of point-to-point communication in these exascale mini applications happens only within a small subset of ranks, independent of the communication pattern. Next, in the second part of this work, we are looking at the network layer. In order to do so, this requires a model to derive some basic network features. This model-based approach ensures that no simulation or replay of traces is needed. However, it provides also no temporal information. This means the results do not provide any insights about message interfering, and no performance evaluations are possible with this model. To perform static network analysis on these applications, we use a simple model that includes basic network metrics such as routing, number of links, bandwidth, or packets. For our studies, we have modeled 3 different topologies: the 3D torus, the fat tree, and the dragonfly, as the most used topologies in supercomputers at the top 500 list. And as routing, we have selected shortest path routing for every topology. This has several advantages. First, it is deterministic, which is good for static analysis. And also, since we have no traffic flows and no congestions on the network, no load balancing is required here. And if we use shortest path routing, we can further emphasize the topology characteristics. Firstly, at the network layer, we are looking at multicore effects. This study investigates how an increasing number of cores per socket affects the overall network traffic. We are only considering applications with more than 1000 ranks to provide useful information. Furthermore, we assume 1 rank per core and an incremental mapping, so rank 1 is mapped to node 1 or to core 1, and rank 2 is mapped to core 2, and so on. And these studies also include collective communication. The plot on the right side depicts the trends for multiple applications. On the x-axis you can see the number of cores per socket, and the y-axis indicates the relative share of network traffic that is still transferred over the interconnection network. The remaining part of the traffic is just exchanged within one node. Surprisingly, although the traffic volume decreases for almost all cases, all workloads seem to reach a plateau at 8 to 16 cores per socket as indicated by the red box. Slight variations in the further cores, as shown by the Lulesh or crystal router workloads, are probably caused by mapping effects. For example, selectivity has shown that there are heavily communicating subsets of ranks. If these subsets are split up in a certain configuration, this can raise the network traffic again, even if there are more cores per socket. The fill boundary application is especially notable since it reduces the network traffic to almost 0 at 8 ranks per socket. In general, it is surprising that 8 to 16 cores per socket are sufficient for reducing network traffic, and further scaling the cores per socket doesn't provide any additional benefits here. The two next metrics we are looking at are network distances in terms of packet hops and average number of hops, and utilization. The first one is determined by the routing, and the second one by the overall traffic volume and the topology. Packet hops are a useful indicator for the total amount of traffic on the network, while the average number of packet hops is more suitable to compare different topologies, since packet hops are highly depending on an application's communication injection rate or on the overall traffic volume. The utilization, on the other side, is a measure on how busy the network actually is by transmitting this traffic volume. This considers also network distances, so the traffic volume increases for every hop that is performed on the network. We selected a bandwidth of 12 GB per second, which is rather low for today's interconnection network. First, we are looking at the average number of packet hops for different topologies and different applications. For comprehensive comparisons, please find data in the paper. However, this graph is particularly useful to show some trends here. Again, on the x-axis, there are all different configurations sorted by the number of ranks, and the y-axis depicts the average number of hops. For each application, there are 3 bars in different colors that depict the 3 different topologies. At the left side, you can see for every configuration smaller than 265 ranks, the torus provides always the lowest network distance, except for Crystal Router and Snap. For larger configurations, the increasing diameter of the torus becomes the dominant effect, and the network distances for the torus increase significantly. And the factory provides the lowest diameter for the following configurations. It is rather surprising to see that although the Dragonfly is always considered as a low diameter topology, there's only one configuration in which the Dragonfly provides the smallest network distance. However, this probably changes with larger configurations due to the fixed diameter of the Dragonfly. The particular design of the Dragonfly with small groups in this work is also not very beneficial for these issues, which is also backed up by the fact that 90% of the overall messages have used a global link. However, we are using shortest path routing here, which reduces also the network distances compared to the often used adaptive routing in Dragonflies. Last, we are looking at the overall network utilization. It stands out that none but one application actually uses the network more than 1%. This finding reflects the trend on the software side to rather avoid communication because of potential high latencies. Another issue that is not considered here is the bulkiness in an application communication pattern. Even if there's only a small amount of traffic, if this traffic occurs for all ranks at the same time because they exchange data after a long computation period, for instance, this can also stress the network. However, this overall very low utilization indicates that networks are very suitable for energy savings where idle periods are exploited. So let's summarize this work. We have introduced 2 new metrics to quantify communication patterns and locality in MPI traces. While ranked locality is useful to derive certain communication patterns, selectivity indicated that there are only small subsets of ranks that are heavily communicating with each other. This suggests that an advanced mapping which identifies these subsets and takes them into account could further reduce the overall network traffic. At the network level, we have shown that 8 to 16 cores per socket are sufficient to minimize the network traffic. Furthermore, for small applications, the 3D torus provides the best network locality, while for larger, the factory is the most beneficial. Independent of the used topology, there is only 1 out of 15 applications that actually uses the network more than 1% of the execution time. However, there are no implicit correlations between the application and network level metrics so far, although correlations between rank and network locality would be especially useful, for instance, to avoid the usage of a network model. Last, here's a short outlook about the next step in context of this work. Rank locality is highly suitable to identify nearest neighbor communication patterns. To widen this by other kind of communication patterns, the effects on rank locality and selectivity need to be studied. Further metrics that quantify communication patterns could help to draw a comprehensive picture of all communication aspects. This would not only be useful to avoid complex network simulations, but also help to gain deeper understanding about different processes in the network. And last, the findings of small communication subsets in point-to-point communication could be used to design better mapping policies that take these subsets and special topology properties into account. Thank you for your attention.